Our very first example on solving for electric fields due to continuous charge distributions involved a uniform rod, and we found what the electric field would be at this indicated point P if it sits at a distance A away from a uniformly charged rod of length L. And we pictured breaking up the total charge Q into several small bits dq. Well, in this problem, we're going to look at the same rod, but we're going to choose a different point. Okay, so same length, same total charge. We want to know in this case, what's the electric field if point P is moved to a location along the y-axis. So let's look at this more carefully. There's going to be some contribution to whatever the total electric field is at point P. There's a small contribution to that total field, dE, that points in this direction due to the charge dq that we've indicated. The distance from the charge dq to the point in question is lowercase r. Then we can define a couple other variables, x, y, and let's also define an angle theta between the electric field component vector and the y-axis. Okay, so again, from symmetry, as we've seen in some previous problems, if I draw a counterpart to that dq on the positive x-axis, we know there's going to be a contribution to the electric field that points up and to the left instead of up and to the right. And so the horizontal component to that vector and the horizontal component to the other vector we've already shown are going to cancel out. So it's safe to say that the total electric field can be found not just by summing up all the contributions, but more specifically all the contributions that represent the components along the y-axis. And the way we've defined the angle theta, any component along the y-axis is adjacent to that angle. So we're going to think about the trig function cosine, right? In other words, if we sum up all of the dE cosine theta, we'll have what we're looking for. Let me copy that again down here. Step 1. There we have it. Okay, so let's be clear what all our variables are one more time. So we see dE. Let's also draw in dE subscript y. If this angle is theta, so is the alternate interior angle, y, x, r, dq. dq takes up some very infinitesimally small length along the x-axis, so we'll call it dx, and there's a uniform linear charge density. That's either the total charge q over the full length L, or, right, you know what I'm going to say, it's also dq over dx, yeah? The amount of coulombs per meter is calculated to be the same value regardless whether you look at the whole or you look at just a piece. Let's make some substitutions. In step 2, of course, we can replace dE with k dq over r squared. There's going to be some substitutions along the way to get this into calculus of a single variable. So we don't have to really even look at the calculation of the charge density as total charge over total length. If I cross multiply by dx, we can say that dq is lambda dx. There we go. And now we've got the integral of k lambda dx over r squared cosine theta. Let's think about this. If we choose, let me go back to the top picture. Let's just pick a different dq and see what changes. Obviously, the value of r for this one is greater. The value of x is greater. The value of theta is also greater. So all of these variables change. The one thing that stays the same is y. No matter which dq we look at, the value of y is going to stay the same. So we're going to lean on that to help us make substitutions. Okay. So let's just look at this right triangle and state all of our trig functions here. If I took the cosine of that angle, the adjacent over hypotenuse would be y over r. We take the sine of that angle, that's going to give us opposite over hypotenuse, so x over r. Tangent of that angle is going to give us x over y, opposite over adjacent. So we can say x is equal to y tangent theta. So what are the constants? What are the variables? Y is a constant. Theta varies with x. So we can take the derivative of x with respect to theta, and this is going to give us y secant squared theta. Or in other words, dx is y secant squared theta d theta. So that's going to help make one substitution. Let's see. R is also a variable. However, if we use this expression, we can rearrange and say R is equal to y divided by cosine theta. All right. So in step 4, we have E equals, let's pull the k and the lambda out of the integral, k lambda times the integral of, so we are left with a dx, but we substitute that with y secant squared theta d theta. And then we've got r squared in the denominator. So if r is y over cosine theta, then of course r squared is y squared over cosine squared. So y squared over cosine squared theta. And then we still have this cosine theta. Okay. Beauty. Now there's really only one variable, right? Theta is a variable, but y is a constant. And notice that one of these y's is canceled out. So in step 5, we get E equals k lambda over y times the integral of, let's see, we've got a cosine, we've got 1 over cosine squared in the denominator. And then we've got this cosine here. So I guess we have secant squared theta, cosine cubed theta, d theta. And isn't secant the same thing as 1 over cosine? Right. So, boy, this really simplified a lot. Who knew? E is equal to k lambda over y times the integral of cosine theta d theta. What are our limits of integration? Well, the very first dq we have to account for sits at the largest possible angle theta. And as we imagine breaking the total charge q up into more and more little bits, as we progress towards the origin, theta approaches 0. And then we can continue moving past the origin and account for everything up until, again, we've reached this really large angle. Or we could just say we're going to integrate from this largest possible angle, we'll call it theta maximum, up until theta equals 0 degrees, and then just rely on the symmetry of it. So we can double the value if we only use limits that take us halfway to the length of the rod. So in step 7, we introduce the number 2, because we're going to change the limits from theta equals negative theta max to theta equals positive theta max, right? So we're integrating from theta max to 0 degrees and then doubling the result. Of course, the integral of cosine is sine, so we have E equals 2k lambda over y times sine of theta max, minus sine of 0, right? But that gives us 0. So there's our result. E equals 2ky over lambda sine of theta max. Now what if the rod goes from this long, so there's the distance y compared to the distance L. So basically as y becomes not just greater than, but much, oh, I'm sorry, the other way around. As L becomes much, much greater than y, that creates a change in what this maximum angle theta would be. In fact, if we go to this extreme case where the rod extends beyond the width of the screen, keeping the value of y the same, what is this angle theta approaching? That means theta max is approaching 90 degrees, or pi over 2 if you prefer. And the sine of 90 degrees is equal to 1. So as the length, we can either say as the length approaches infinity, or alternatively as the length just becomes much, much greater than the value of y, then the equation just reduces down to E equals 2k lambda over y. Now in a previous lesson I suggested there's going to be another way of solving for electric field due to continuous charge distributions, known as Gauss's law. I think that was for the, I said in the case of finding the electric field due to a charged disk at some point along the x-axis, one way we can do it is the method we did, which takes what I might call some brute force, right? In other words, we divide the total charge q up into little bits dq. Now in this case of the disk, our dq's were in the shape of charged rings, where in this case our dq obviously is more in the shape of little pixels, right? It's very important that when you do these derivations that dq is something that you picture. You know the shape of your element of charge. So the method we did of breaking it into these dq's, I refer to that as the brute force method. Gauss's law gives us a more sophisticated or elegant method for finding electric field. And it turns out we can use Gauss's law also in the case of the infinitely long rod, and we should get the same result. So just make note of that and keep that in the back of your mind as we progress into the next unit of study on Gauss's law to see the result we get is consistent with the result we found from this brute force method. As always, thanks for watching.